I think there is one student online, James. Can you hear me, James? Just say yes in the chat box if you can hear me. Yes, excellent. So James can hear me, so we can start. Okay, so it's the recording. Okay, so we're continuing with the moment distribution method. Okay, how are you finding the pre-recorded sessions? Okay, helpful. Yeah, how many people are really watching them before the session? Okay, most of you. Yeah, please do if you don't, because it's almost like a repeat, because I covered it with the previous cohorts. Slightly different, but it's more or less the same. Okay, so I think the best way to illustrate the moment distribution method is through a simple example. So I'm going to take you through an example from A to Z on how to use the method, how to obtain the bending moments, how to draw the bending moment diagram, and then how to obtain the intermediate values over a span. Okay, so we'll do the whole thing today. Okay, and the example I have, so it's moment distribution. So moment distribution method. Okay, and the example we have is this one here. So I'm going to take the same example as in the pre-recorded session, okay? So those of you who have watched it, they can relate to this, okay? So we have a span ABC, okay? It's fixed at A and fixed at C. It carries a concentrated load at mid-span of AB of 10 kilonewtons. So it's 10 meters span, and on BC, we have a uniformly distributed load of 2 kilonewtons per meter. And the span is 12 meters. We assume that the rigidities, the flexural rigidities are the same. So the flexural rigidity for AB is EI, and the same for BC. They can be different in practice. You could have a continuous beam where one span is different to the other. You know, for example, if they have different cross section. Yes, you could have a cross section. In that case, the EI will be different. Or I just remind you, E is Young's modulus. Okay. A here is Young's modulus, and I is the second moment of area. Okay, so I mean, in this particular example, we assume that the AI is the same for both beams. Okay, and the question here for this particular problem is to draw the bending moment diagram for this beam here, an annotated bending moment diagram using the moment distribution method. Okay, now this is as I explained last week, this is a statically indeterminate structure. It's statically indeterminate, okay? What's the degree of redundancy? Do you remember what we said last week? What's the degree of redundancy? 5. We have 3 reactions at A, 3 reactions at C, that's 6, and then you have 2 possible reactions at B, okay? Because it's not a roller. If you have a roller, it's 1 reaction. If you have a support like this, it's 2 reactions. If you have a fixed support, it's 3 reactions. So we have 3 plus 3, 6, plus 2, 8, minus 3 equations of equilibrium, 5. Is that clear? So the degree of redundancy here is 5. So it's highly indeterminate, okay, with the degree of redundancy of 5. Okay, so we have, if you want, we have 8 unknown, okay, reactions minus 3 equations of equilibrium. Okay, so we have 1 unknown reactions minus 3 equations of equilibrium, 5, which is the degree of redundancy. Is that clear? Is it clear, please? Yes? Yeah. So all you have to do basically, if you have a 3-span or a frame or whatever, always count the number of, how many reactions you have, and then minus the 3 equations of equilibrium. It's very simple. And that will tell you the degree of redundancy, meaning how complex it will be for the beam to be, solved by hand. So the higher this number 5, the higher it is, the more complex is the structure. Okay. So let's make a start. So remember what was the first step? Step 1. If we want to use the moment distribution, what's the first step we need to do here? Do you remember? Split up, exactly. So what we need to do, we are going to take the beam, okay, split it up into beam cases, beam-ended, fixed-ended cases, okay? So we have AB here, and we have BC, okay? So this is what we're doing, split it up into 2. And when you split it up, remember, please, the rule is the intermediate support here becomes fixed. Any intermediate support becomes fixed when you split it up, okay? The end supports here can remain as they are, but the intermediate supports, when you split it up, become fixed, like here. Okay, so this is what we have now, with the load here and the UDL on that side. Is that clear? So we have W 10 and W little w 2 kilonewtons per meter. This is kilonewtons, okay? 5 meters. 5 meters and 10 meters. We have A, B, and B, C. Beg your pardon? BC is 12. Oh, sorry, 12, yes. Okay, so this is what we have now when you split it up into 2 beam cases. Is that better, or isn't it? Is that better? Okay, thank you. So we have got now the 2 beam cases. So next step, what's the step 2? Do you remember? Yeah. Have you got your table still with you? Yeah. Check the table. I've given you a table last week, or if you haven't got it, it should be on your aula. Yeah, so there is a fixed and moment table, which will be given to you in the exam. So you don't have to memorize that by heart, okay? So all you need to do is have that table with you. So let's start with AB. So step 2, fixed and moments. So fixed and moments is the 3rd step. So we do beam by beam, case by case. So we start with AB. So this is AB here. Okay, and we have a load W, 10, and the span is 10 meters. Okay, and it's in the middle, okay, mid-span. So we have the fixed moments. At A we have a bending moment this way, anti-clockwise, and B we have a clockwise moment like this. These are the moments at the ends. You agree with the directions? Clear? Yeah. I mean, remember, if the way to remember the directions is this: if you have a beam and you load it, okay, it's going to try and bend like this, isn't it? So what's going to happen? The supports here will try and prevent it. Yeah, because these are reactions, these moments, okay? So I repeat, if you have a force, if you have a load pushing down the beam, it's going to bend like this. So to prevent that bending, the moments here will try to prevent that. So you have got moments going this way, right? Okay, so and this is the fixed end moment at A, so we call it FEMAB, and this is the fixed end moment at B. Okay, BA. Always the first subscript refers to the joint. So when we say FEMBA, BA, that means at joint B, and this is at joint A. Is that clear? And then you get the values straight away from the table. Okay? So what is FEMAB from the table? Minus WL over 8. If you know it on top of your head, fine. If not, don't worry, okay? You can use the table. So we have got minus WL over 8, which is minus 10 times 10 over 8. And I believe that should give 12.5. Is that okay? So we have minus 12.5 kilonewton meters. Please always put the units. I hate when I see answers without units, please, okay? So, and then FEMBA will be exactly the same with the plus, okay? It's plus 8 WL over 8, so it's 12.5 kilonewtons meters. So that's for AB. Is that clear? Okay, now we do BC in the same way. So this is BC here now. Okay. We have a UDL of 2 kilonewtons per meter. We have a span of 12. Okay, similarly, we have got CB, and FE and FEM, fixed moment at BC. Okay. So again, from the table, so what's the equation now? WS square over? Yes, WS square over 12. Everyone okay? Do you agree? From the table, so minus WS squared over 12. So we have minus 2 times 12 squared over 12, which gives 12 and 12 cancel. So we have minus 2 times 12, so minus 24 kilonewtons meters. Okay? Is that all right? Yeah, similarly, FEM, the fixed moment at C will be the same with the plus. So plus 24 kilonewtons meters. Please, if anything is not clear, just stop me. Yeah, just raise your hand, ask the question. Is that okay? Okay. So now we've got, that's the first step, right? So we've done that. Step 2. So what's the second step? Do you remember? Sorry. Okay, so if you put it back together, okay, so this is what, 3 here. So if we put it back together, this is what we have. Okay, we've got, at A, we have 12.5, remember the convention. When you say minus here, that means it's anti-clockwise, okay? So we have anti-clockwise 12.5, we have clockwise 12.5, we have minus 24, so that's anti-clockwise here. So we have 24, and finally at C, here at C, we have clockwise 24. And as you can see, when you try and put it back together, what we have an imbalance here. We have an out of balance. Can you see that? Yeah, I mean, this should be equal and in equilibrium, okay? This should be in equilibrium here, okay? Because you've got if you have a continuous beam, the moment left and right at the intermediate joint must be equal and opposite, okay? That's one of the conditions of equilibrium, is that the moments at an intermediate joint must be equal and opposite left and right, okay? Whereas here you can see that we have got an out of balance here. We have an out of balance. We have an out of balance of how much? Do you agree? It's minus on this side, plus on this side. So we have 11.5 with a minus. Okay, it's an out of balance of 11.5. Okay. Oh, it's minus, sorry. Plus 12.5 minus 24. Anti-clockwise plus, anti-clockwise minus, always, okay? So we have an out of balance of 11.5 with a minus. Is that clear? So that this out of balance, we need to get rid of, okay? That must be in equilibrium, okay? We need to get to a position, where the out of balance here is 0 at the end. Is that clear? So the purpose now is to balance this out of balance here, and we do it in 2 stages. We balance it, in other words, at the joint itself, but then the adjacent joints will take some of the burden, some of that. Are you with me? Yeah, it's like you have got everything here concentrated, but then you want to distribute so that the other joints can also help and take some of that. Is that clear? Yeah, and the way we do that is using what we said. Do you remember what we said we used last week? Distribution factors. It's the distribution factors that will help us decide how much each member will take, okay? And then we carry over to the joints at the end. Okay, so that's the next step is to calculate, to determine the distribution factors, which I'm going to explain here. So we determine the distribution factors. Okay, so for the distribution factors, we have three joints, isn't it? Yeah, we have 3 joints, A, B, and C. Yeah, and we calculate the distribution factor for each joint. Okay, because you've got the moments at the joints. Okay, so we start with joint A. What do you remember the definition last week for distribution factors? Sorry? Stiffness, yes, stiffness. So a distribution factor at a joint, okay, a distribution factor at a particular joint is equal to the stiffness of the member connected to that particular joint divided by the sum of all the stiffnesses for all members connected to that joint. Okay, so here we have only one member. Can you see here? Joint A, we have only one member connected to A, isn't it? There is only one member. There, I mean, you can imagine there is a wall here and a wall there. So your beam is connected to a wall or could be a column. Yeah. So but in terms of the member itself, there is only one member connected to A, and that's the member here, AB. And then you have got something infinitely rigid. We just assume that we've got something infinitely rigid here, where the beam is connected, which could be anything, okay? Because it's fixed, so this has to be infinitely rigid, very rigid. So therefore, if we use the definition, so we have the distribution factor, joint A, B. So that means it's the distribution factor at joint A. Okay, it's the distribution factor at joint A of AB, of member AB. Okay, so it's equal to the stiffness of AB. What is stiffness of AB? EI over the span. Yeah, so it's EI over the span, in this case, 10, divided by stiffness of all members connected to A. So connected to A, we have only one member, so therefore it's EI over 10 plus the stiffness of whatever is here. We said it's infinitely rigid, so this will be something really large, okay? Because it's rigidly fixed, okay? So we have something here really infinitely rigid. So if so basically, if you divide by something very large, what do you get? Yeah, always. Yeah. Regardless of what values we have here, that will be 0 for a very large value here. We do the same for joint B now. Okay, now we go to joint B. Joint B now, we have two members connected to B. We have BA and BC. We have two members. We have BA and we have BC. So we calculate the distribution factor for joint B for member BA and the distribution factor for joint B but for member BC. Because that joint is shared between the two members, okay? Because joint B belongs to BA and BC. So we use the definition again. So we have stiffness of BA. What is stiffness of BA? Just look at the figure here. Yeah, BA, it's EI over 10, yeah, divided by stiffness of all members connected to joint B. So we have EI over 10 plus EI over 12. What you can see here, you can see that the EIs it will always cancel, always. So what you have, effectively, you have 1 over 10 over 1 over 10 plus 1 over 12, okay? Which I believe, please do check it if you've got your calculator. Or if you want to leave it as a fraction, you can do that, but I've calculated it as 0.55. Yes? Okay. I think it's 6 over 11, isn't it? I've just done it in my head. Okay, so it's 6 over 11. So if you want to leave it as a fraction, you can do that. Okay, I put it here between bracket, 6 over 11. When you simplify the, you make it common denominator, it gives you 12 over 22, which is 6 over 11. Okay. Now, similarly, we do the same now for BC. Okay. For BC, we have stiffness of BC, EI over 12, divided by sum of all stiffness of all members connected to joint B. So it's the same, EI over 10 and EI over 12, okay? Which gives 1 over 12 over 1 over 10 plus 1 over 12. What is it not 0.45? Sorry? Yeah, it will be 5 over 11. Because what you get in this case, you get 10 over 22. When you put it common denominator, you get 10 over 22, simplify, which gives you 5 over 11. What do you notice here? The sum is 1. The sum is 1, okay? So here, we've got these two here. So we have DFBA plus DFBC is 1. Remember this. When you have got intermediate joints like this here, that is always the case, that the sum of the distribution factors at that joint will always be equal to 1. Always. So the sum of the distribution factors at an intermediate joint will always be 1. So that's a very good way to check your answer. Okay. But let me say something important here. When you have an intermediate joint, the sum of the stiffness, the sum of the distribution factors must be equal to 1. All right? But if the sum is equal to 1, it doesn't mean that your answer is correct, that your answers here are correct. If you don't get 1, your answers are definitely wrong. But if you get 1, your answers, it doesn't mean that your answers are correct. Does it make sense? Because I can show you examples later on where if you make a mistake and it's in both, you could have the sum equal to 1, but because the individual answers for each one are actually incorrect, so you get a total which is not, which you get a total equal to 1, but the answers are incorrect. I don't know if I'm making sense or not. Yeah. So not getting 1 it will tell you that you're wrong, at least, and then you can check your answers. But having a 1 here, it doesn't mean that you're correct. And I'm going to illustrate it in an example later when we have different ends here. For example, a roller or a simple support, and that can show you that getting 1 is not always doesn't always mean that you are correct. Okay. Anyway, so at least here we can say fine. Moving on to joint C, the final joint C. Well, joint C is really the same as joint A, isn't it? It's fixed, and there is only one member and the wall on the other side, so it will be exactly the same. So DF CB will be EI over 12 divided by EI over 12 plus a very large stiffness for the wall, which gives 0 as well. Any questions, please? Are the distribution factor calculations clear, please? If anything is not clear, let me know. Yeah, these are the 2 important steps: getting the distribution, the fixed moments, and the distribution factors. These are the key 2 steps. Once you've done that, I can show you now that the rest is really straightforward. But you must get the fixed moments from the table. That's not a problem, correct? And then you need to think about the distribution factors, determine the distribution factors, and these are the 2 key steps here, okay? So what do we do now with the distribution factors and the fixed moments? Now I've got everything. I know the moments at the joints. I know the distribution factors, and the distribution factors are the ones that will help me now to balance this out of balance moment and distribute to the adjacent joints here. Okay. There is only one thing I need to explain before we move on. So here we have an outer balance of minus 11.5. Okay. And that's because left of B and right of B here, we have got different moments. Okay. Now, the first step is to balance this moment here, but then the adjacent joints will take some of that moment. Does it make sense? Yeah. I mean, if I have, let's say if I take this here, imagine this is your beam here, okay? And I load it. You agree, if it's fixed at the ends, but the ends it will take some of that moment. You agree? Yeah, you will feel it. So some of that will go to the other joints, okay? How much do we give, how much the joints here will take? I'm not going to go into a two-page, to prove it to you, but I can tell you they will take half. They will take half. If you have got the joints fixed, they will take half. You carry over half to the joints. I'm going to explain it now in the table, because just remember that the what we call the carryover here will be half. Okay, and we can prove it. And I'm going to upload the evidence to prove in Aula if you want to read through it. I'm not going to do it here. It's a lot of theoretical work. And because you didn't do, have you done Macaulay's method before? Has anyone heard of it? No? Moment area method? Slope deflection method? Yeah, that's why I don't want to invest time to show you that it's half, because you haven't heard of the the methods before, so that I can explain it to you. Okay, so all I'm asking you now is accept that the carryover factor is half. If you want to see the evidence, the proof, it will be in Aula, okay, in one of the sheets. So let's do it. How do we do that now? We do that. Let me get a new. Okay, I think there is enough space here to do it. So we do what we call the moment distribution table. I need your attention here, please. This is what I need, really, I need your attention, okay? So now we draw a table. Okay? In the first row here, we put the joint. Okay? In the second row, we put the member. In the third row, we put the distribution factor. And the fourth row, we put the fixed end moment. Okay? So joints, member, distribution factor, fixed end moments. How many joints we have? We said we have 3 joints, A, B, and C. So we have A, we have B, and we have joint C. Okay, how many members are connected to joint A? 1. So we have 1 member here, AB. B, how many members? 2. We have BA and BC. You agree? And finally, for joint C, we have only 1 member. Okay, we have 1 member at C, and that's member CB. Okay, CB. So we have joint A, we have AB. For joint B, we have BA and BC. And finally, at joint C, we have only 1 member, member CB. And that's what we have. Okay, now the distribution factors, look here. For AB, we have 0. So for AB, we have 0. For BA, we have 6/11 or 0.55. For BC, we have 0.45. And finally, for CB, here we have for CB, we have 0. Fixed moments. Again, we have calculated earlier. For AB, we have minus 12.5. For BA, we have plus 12.5. For BC, we have minus 24. And finally, for CB, we have plus 24. So this is our input data. Is that clear? So we have the joints, the members associated to the joints, and then we have the distribution factors at each joint for each member, and finally the fixed end moments. Right, okay, now this is where the real fun starts. Okay, we have here, we have an out of balance of minus 11.5. You agree? Yeah. Please pay attention here. I'll give you time to write it down. Just follow with me, and then I'll give you, time to write it down. So we have an out of balance here of minus 11.5. Clear? In order to balance it, in order to make it equal to 0 in equilibrium, how much do I need to add? Exactly. So I'm going to do it here this way, but in the future you will see you don't have to write everything down. So here we need an 11.5 to actually make it in equilibrium. So now I'm going to balance this. Okay, this is at the joint. So I'm going to balance it at that joint and give a portion to each member. So how much do I give to member BA here? You see, you've got two members, BA and BC. So at joint B, here, we have BA and BC, isn't it? So I'm going to balance this moment by giving 0.55, a portion of 0.55 of that to BA, and a portion of 0.45 of that to BC. In other words, 11.5 times 0.55, can you tell me, give me the answer? 633. Yeah, let's say about 633, yeah. It's plus, remember? So this is balancing, okay? And then we balance here. So 11.5 times 0.45. Is it 517? Okay. So I repeat, you multiply 11.5 times 0.55, it gives you 633. 11.5 times 0.45 gives you 517. What do you notice if you add these two together? What do you get? Exactly. Okay. So this is the balance. So now that moment at B, I have now balanced it. I have balanced it at B by giving 6.33 to BA and 5.7. But what do you do then? Some of this moment here will be carried over to, so this is what we say carry over. So we carry over, how much did we say? Yes, so we carry over half to A, 6.33 divided by 2 is, I think, 3.17. Yeah, and then you carry over half to joint C, so 517 half is 259. That's it. That's it. Now, because there is nothing else we can do, so what do? We draw a line here. We draw a line, and what you need to do, you need to add the moments here. 12.5 minus plus 317, 12.5 plus 633, minus 24 plus 517, okay, 24 and 259. So we add these moments together. So what is 12.5 minus plus 317? I've got 933. Is that correct? So minus 12.5 plus 317 should be minus 933. Then you do 12.5 plus 633. I've got 83. Is that correct? Yep. And then I do minus 24 plus 517. I believe it's minus 1883. And finally, 24 plus 259, I've got 26.59. Okay, so these are the moments. You add the moments together, not the balancing or the out of balance, because that's just for the illustration, yeah, to show you what's happening. So you add the moments. So what do you notice here? What do you notice at joint B, which is the intermediate joint? Equilibrium. So what's the out of balance now at B? 0. That's it, job done. Because that's all we wanted. We wanted to get rid of that 11.5. And it's gone. So now we have equilibrium here. You see how effective it is, the method? Once you've done it a few times, All these steps that we've done, it's taken us maybe half an hour to do, you can do them just in 5 minutes. It's so simple. You calculate fixed moments from the table, you do your distribution factors, and you do your table like this, and it's job done. You get equilibrium, and you have got the moments everywhere in your member. So it's a very, very powerful method. Remember, this is a 5-degree indeterminate structure. 5 degree, so it's quite high, the degree of redundancy, and we haven't invested a lot of time doing it, as I said, because I'm explaining, but if you do it on your own after a few times, it doesn't take you 5 minutes really to do that. Is that clear? So it's a very powerful, really very powerful method, that you can use for highly, for hyperstatic, for highly indeterminate structures. Any questions? Okay, so now we've got equilibrium, and that out of balance has gone now. Okay, we have out of balance here 0. Okay. So the next step now is to take these moments here and draw the bending moment diagram for the beam as a whole, okay, which I'm going to do here. So bending moment diagram. So bending moment diagram and intermediate values, okay? So the bending moment diagram and intermediate values. So let's take our beam and see what's happening now here with this. So this is the beam here, A, B, C. Okay, at A, look here, at joint A, we have minus 933. Minus means anti-clockwise. So we have here an anti-clockwise moment of 9.33. At B on BA, okay, at B on BA, we have clockwise 1883. So clockwise here, 1833. Then we have anti-clockwise here, 1833. And finally at C, we have 26.59 clockwise. Okay, and compare these two. Okay, see where we started, and this is where we ended up. Okay, so the out of balance has gone, it's in equilibrium, and some of the moments have gone to there. Okay, it's as I said, it's an iterative, and it's very, very effective, very efficient, even if you have a very high number of redundancy. Okay, so now we've got these moments here. This is I need your attention here. We use a convention. When we draw the bending moment diagram, we use the convention, and you need to be consistent. And I'm going to use the convention that most of the textbooks are using. Okay, unless you use a French or American book or whatever, they have got a strange convention where the moment, it's the other way where we do it in the UK. So I'm going to explain to you, if you're using a textbook here in this country, the convention we use is this. We plot, we draw the bending moment value on the side of, of the member where there is tension. For example, if you take joint A here, where is the tension, at the top or at the bottom? What do you think? So this, yeah, I mean, look, this is, you've got a moment 9.3 going this way, isn't it? So you have tension at the top, can you see that? And then it's compression at the bottom. So we have tension at the top. Where is the tension at B here? You agree? Top or bottom? You agree? Stop. There? Top. Okay. It's just happened that in this case, the tension is at the top everywhere at the joints. It's not always the case, I can tell you this. We'll see this in some more examples, okay? So we have now identified the tension is at the top, and you plot your bending moment value on the side where there is tension. So the other thing you need to remember that there is a point load here, and there is a UDL there, okay? Don't lose sight of that, of the loading. So now I'm going to do this. Okay, now please attention. We have 9.33 at the top. Okay, so we have 9.33 at the top. We have 18.33 at the top. So we have 18.33, and we have at the top, we have 26.59. Okay, I mean, I'm sorry, my drawing is not to scale. So what, and then what do we have? Between A and B, we have a point load, so it's going to be linear. Okay, and between B and C, we have a uniformly distributed load, so therefore the bending moment diagram will be parabolic. Is that clear? And that's the shape of the bending moment diagram, correctly drawn. Okay, in other words, you follow the convention for the sign of the moments, and you follow the convention on how you draw the bending moment diagram, and then you get the correct shape of the bending moment diagram. If you don't follow the convention, your bending moment diagram would be all over the place. So you could have this here, down there, or whatever, okay? So please make sure you do follow the convention. And that's the bending moment diagram for this beam. What's left? Yeah, the intermediate values, okay? So the intermediate values, we need to determine the maximum moments, and we need to determine the position of these points here. These points are what we call the points of contraflexion, and these are the points of maximum moment. Okay. I would just like to open a bracket here. These points of contraflexion correspond to what? Sorry? Yeah, but what does it correspond to exactly? The bending moment is 0, isn't it? You agree? So the point of contraflexion corresponds to moment 0. What it actually means, it means that this point here corresponds to a point where the sign of the bending moment changes. Yeah, from positive to negative or vice versa. So the bending moment changes. How many people here work in a design office? Are you familiar with designing reinforced concrete beams? Yeah? Or do you know about reinforced concrete beams? Have you seen a reinforced concrete beam before? When you have a reinforced concrete beam with loading, the reinforcement, there are two types of reinforcements. There is what we call a compression reinforcement, and there is a tension reinforcement. In other words, there is reinforcement that will resist the compression, and there is reinforcement that will resist the tension. Knowing the exact position of these points is very, very important in design. Are you doing design this year or next year? Or you're not doing design? Are you doing design? So you will be doing design, yeah? So when you do design of concrete, you will see what I'm talking about. You will understand. So the point of contraflexion, these are the points where the reinforcement bars will be swapped over. In other words, the reinforcement bar in tension becomes in compression and vice versa. You see what I mean? So you're having, so for example, from this side to there, that moment is actually a hogging moment. And the moment between there and there is a sagging moment. This is what we call hogging. This is a sagging moment, sag. Okay, and this is hot. Okay, so anyway, what you need to remember, as I said, is that for this particular point here, if you are talking about a reinforced concrete beam, the reinforcement will be swapped over, will change. So the compression becomes tension and the tension becomes compression, because that's the point here. Okay, so that's why in design we actually determine the position of these points here. They are very, very important. Okay, and the moments, the maximum moments, also we need the maximum moments in design. And the reason we need the maximum moment of design, there could be cases where the intermediate moment is actually bigger than the end moments. Maybe not in this case, but there are cases sometimes, depending on the loading arrangement and so on, you could have intermediate moments bigger than the end moments. And remember, when you are designing a beam, you design it for the maximum value, isn't it? You design for the maximum moments. And that's why you need to know what values are these intermediate moments, okay? Because that could be your maximum moment. That could be your largest value, all right? So I'm going to show you how to actually determine the intermediate values for moments and for points of contraflexion. And do stop me if you have any questions. Is it time? Do you want a break? Some people are saying yes. Okay, let's have a, maximum 10 minutes, okay? All right. Yeah, we about 10 minutes, please, no more. Those of you online, Henry, James, etc., are you okay so far? Yeah.
Yes, thank you.
Have you got any questions, those of you online? Okay. Okay, thank you, Zakaria. Hi. Yes. Yeah, we are just having a break, okay, for about 10 minutes, and then, 8 minutes now, and then we resume, okay? So I'm going to mute myself. Oh wait, I think everyone is back, isn't it? Yes? Okay, all right. Okay, let's continue, please. Let's resume. Yeah. So, in order to determine the intermediate values, okay. So, in order to determine the intermediate values, what we need to do, we are going to analyze each beam in isolation. Okay. So we take AB, and then we analyze it in isolation, and then we take BC, and we analyze it in isolation, and that will allow us to determine the intermediate values. Okay, so let's start with beam AB. Okay, so we start with beam AB here, and that's AB. Can you see that? So what we have, this is AB. We have 933. We have clockwise 1833. Yeah. Is it 83? No, sorry, it's 83, isn't it? 83, sorry. Okay, so we have 83, 1883, okay? And so that's A, and then we have the load here. What was the load? Was it 10? 10. So we have 10 kilonewtons meter, 10 kilonewtons, sorry, okay? And the span is, we have 5 and 5 meters. So this is beam AB. You see? Now, in addition to the moments at A and B, what else do we have at A and B in addition to the moments? We have reactions. Do you agree? We have also vertical reactions here. So we have a reaction there and there. So I'm going to call this here, I'm calling it just like moments. So I use the same terminology. So we have the reaction at A, AB, and VBA. So we have VAB and VBA, and these are the reactions at A and B. How do you determine the reactions? Sorry? Yeah. Yeah. Let me tell you this. I mean, you do have 3 equations of equilibrium, but I can tell you this now, okay? If you want to get your reactions always right, don't use vertical equilibrium. Use 2-moment equations. Okay, use two moment equations and then use the vertical equilibrium to check your answers. Does it make sense? Okay, so instead of using moment equilibrium and vertical equilibrium, don't do that, because if you make a mistake, you will not know, you won't know. However, if you use two moment equations and then you use the vertical equilibrium to check the answer, you are guaranteed that your answers are correct. And this is what I'm going to do here. I'm going to take moments about A, and then I'm going to take moments about B, and then I'm going to make sure that I check that these two reactions, when you add them up, will give me 10. And that's always the best way of doing it, is to use two moment equations for equilibrium. Do it all the time, whether you have a beam or frame or whatever, use two moment equations, please, and leave the vertical to check your answer, okay? So we are going to take moments about A. So we take the equilibrium of moments about A. So this is A. Equilibrium, we take clockwise moments equals anti-clockwise. Do you agree? Yeah, so the clockwise moments must be equal to anti-clockwise. Take A here. Give me, what are the clockwise moments about A? What can you see? 10 times? Yeah, that's clockwise. Anything else clockwise? Do you agree? The 883 is clockwise. Yeah, so plus 883. Anything else you see clockwise? No. Okay, equals anti-clockwise. What do you see anti-clockwise about A? So VBA, yeah, times 10, yeah, anything else? Can you see that? That's anti-clockwise, isn't it? So plus 933, that's it. So clockwise equals anti-clockwise. Yeah, so you take your point, in this case A, and any moments about that point clockwise equals to the moments about that point that are anti-clockwise for equilibrium. So now I can add them up. So I have 50 plus 18. Have you got your calculators with you, please? Yeah. Don't trust me, okay? Determine your reactions. I've lost it here. I don't know where I've got it. I did the calculations earlier, but I don't know where I put them. So what do you get for BA, please? So VBA, 5. Thank you very much. 595 kilonewtons. Now we do the same. We take moments about B. And about B, right? Everybody, I'm going to ask you, please, can you write down on your own? I give you 2 minutes. Can you write down here the equation? What do you think moments about B, please? Clockwise moments equals anti-clockwise moments about B. Can you do it, please? We are supposed to have a tutorial session anyway. The first session is a lecture. The second session is the second part is a tutorial. So really, I should be giving you more time to work on your own. Can you do that, please, for me? The second equilibrium equation. So look at B and write down, look at joint B here, okay? Look at joint B and write down all the moments that are clockwise equals to all the moments that are anti-clockwise about B. Just follow what we did here. Do it on your own. It doesn't matter if you get it wrong. At least you make a start, okay? You get it wrong the first time, maybe the second time, but then with some exercise, you will get it correct, okay? Okay, you done it? So about B now, clockwise, what do we have clockwise about B? Look here, concentrate on B, just focus here. What can you see clockwise at B? That's the first thing we see, isn't it? That's clockwise. Anything else clockwise about B? Yeah, the reaction here, because this reaction is, you can see, is clockwise. So we have VAB times 10. Okay, that's it. And then equals anti-clockwise, you can see here B, anti-clockwise, going this way. We have 10 times 5. This load here times 5, and that's also anti-clockwise about B. So we have 933. And please, again, do check for me the answer. I got 4 or 5. That's what I have, yes. So we have 4 or 5 kilonewton. And you see here what I've said earlier about adding them up? When you add them up, okay, check VAB plus VBA equals 405 plus 595 equals to 10, and that is 10 here. Okay, so the two reactions add up to 10. This way you guarantee that your answers are correct. It's very easy to make a mistake, especially when you have some, loading arrangements where you have UDL with 2-point loads or whatever. Yeah, it's very easy. We all make mistakes, but if you do it this way, you guarantee that your answers will be correct. Okay. Now we've got the reactions. What do I do with the reactions? Okay, so I'm going to draw it here just for my own. So I have 405. I have 9, 595. I have 10, 18, and 933. Remember what we are after. We're after this point here. That's what we are after. Yeah, we want to know the position of the points of contraflexure and the maximum moment. Any questions on the reactions, please? Clear? Okay. Let's do this one first. Let's get the moment here. Can you see this moment there? Let me call this point here point D, for example. Okay, let's call this point D. What is the moment at D? What is the moment at D? I'm going to do this slowly, so please follow with me. Look, this is point D here, and you want the bending moment at that point D. Okay, so I'm going to cover everything. I'm going to concentrate on the left side here. Okay, so I'm going to concentrate on the left side. Now, first of all, the moment at D here will be this reaction times 5. Do you agree? Yeah, so we have 4.05 times 5, okay? And this moment is going, is going in this way here. So we have the reaction. Okay, we have the reaction here. About D gives a moment of 4.05 times 5. Then we also have this moment. What's the sign of this moment? Yeah, negative. So we have 9.33. It's going down like this. So we have 9.33, and that's the moment at D. All right. Again, please do check it. I've got 1092. Can you check it, please? 4 or 5 times 5 minus 9, I've got 1092. Yeah, thank you. So we have 1092 kilonewtons meters, and that's the moment at point D. How do we determine now the points of contraflexion here? These 2 points here. Am I going too fast, or the pace is okay? A bit too fast? Okay. So how do we determine these points here? Contraflexion. There are 2 points. There is 1 point of contraflexion between A and, let's call this here D. So we have a point of contraflexion between A and D, and we have another point of contraflexion between D and B, right? So I'm going to take 2 sections. So to determine the points of contraflexion, so to determine the point of contraflexion, first of all, we take a cut between A and D. Okay, that's the first thing. So we take a cut here. And let's call this distance here x. So we take a cut between A and D, and let's take the origin at A and call this distance here x. So we take a cut there. Okay, so we take a cut between A and D. Can you tell me what is the bending moment at the cut here? What's the bending moment there? We have the reaction, isn't it, times x. Do you agree? Yeah. So M will be, so that's the bending moment at the cut, will be 405 times x. Is there anything else? Exactly. Minus 9.33. And that's it. That's the equation of the bending moment between A and D. So I repeat, so we take a cut between A and D, okay? And the bending moment is force times distance. So 4.05 times the distance to the cut here. So 405 times x, okay? And then that's already a moment, so you don't multiply it by distance because it is a moment already. So we have got minus 9.33. Does it make sense? Is that clear? Yeah. What did we say the points of contraflexion corresponds to what? Moment 0, okay? So M equals 0. We have 4.05 x minus 933 equals 0. And that means x is 933 divided by 405. What does it give? I've got 2.3 meters. So 2.3 meters from A. So that's the first point. We have 2.3 meters from A. Yeah, so we have 2.3 meters. So the first point of contraflexion is 2.3 meters. Now, when you are, please, can I have attention here? When you are performing these calculations, always see whether your answers do actually make sense or not. All right? What I mean is this. If I get an answer here of, let's say, 6 or 5.5 or whatever, will you accept it? Why not? Because the maximum you can have is 5, isn't it? It's between A and D. So your answer here definitely has to be less than 5. Then, if you look at the moment at A is 9:33, and the moment at D is 10:22. So these two moments are not equal, but close. So you expect that the point of contraflexion where the moment is 0 will be roughly about the midpoint. Yeah, so you've got 5 here, the midpoint is 2.5. You can see it's quite close. Do you see the logic? Yeah, so always check that your answers actually are making sense. So if you get anything that doesn't look right, don't accept it. If I get an answer here of 5.2 or 6 or whatever, or 7, I will not just close my eyes and accept it. I would just say here, I'll put a note and say, that looks wrong. If you have time, you can go back and rectify it. But if you haven't got time, at least you have said it's, you know it's wrong. And that gives you, awards you a lot of points. Is that clear? Yeah. So now we do, we need to take the, we need to determine the second point of contraflexion here. Okay. And in order to do that, I'm going to take a cut this time between D and B. So I take a cut here between D and B. So the same beam, but this time I'm going to take a cut here between D and B. I'm going to keep the same origin, or you can have the origin from the. Shall we do it from this side? Okay, let's call this X here. So take a cut between D and B. So here put between brackets origin at A, okay? Origin at A here, and here we are taking the origin at B. So we are going to repeat the same thing. So here we have taken the cut between D and B and the origin at B. So I want to know what is the bending moment there at the cut. Okay, now I covered this side here. So what is the bending moment at the cut now? $5.95 times, yes? Do you agree, everyone? Okay, so the bending moment there is 5.95 times x, okay? Force times distance, and then you've got the this moment going this way, so it's minus 1883. And that's the bending moment equation for between D and B. And we do the same, we say for the point of contraflexion, okay, M is 0. No. No, okay, I tell you why. I did not explain it. When you are determining the equilibrium, you can use clockwise, anti-clockwise. Yeah, that's fine. All right, please listen to this because that's very important. Okay, that's an important question. When you are determining the equilibrium, you can use, as we did here, you can use clockwise, anti-clockwise. So you say clockwise moments equals anti-clockwise. That's fine. However, when you take a cut at a section, we use a different convention. And I'll tell you what this convention is. All right? I hope it doesn't confuse you. But the convention we use when you take a cut is that if a moment produces a sagging shape, it's positive. If it produces a hogging shape, that's hogging, it's negative, right? So this is positive, smile, okay? Smile face is positive, sad face is negative. Is that clear? So if you take this reaction, for example, at this end, can you see this reaction? This reaction produces what kind of moment, positive or negative? Yeah, This reaction produces positive or negative? Look, this reaction produces a positive moment or a negative moment? What did you say? Smile. So, positive, you agree. So this reaction produces a positive moment, isn't it? And this reaction also produces a positive moment, according to this convention. And yet, this moment is anti-clockwise, and this moment is exactly. Can you see the difference between the two? So when you're taking the cut, use the sagging, hogging convention when you take a cut. And that's why here we've got minus there and we've got minus there. It's because this moment here, the 1883, is actually making the beam bend this way, which is hogging. So it's minus, right? Whereas this reaction here, makes the beam sag. So it's positive, right? Is that clear or not? You're okay? Yes? Okay. I know it's like two different conventions. Yeah? You have the clockwise, anti-clockwise, and you have the sagging, hogging convention. So M0, we have 595x minus 1883 equals 0, which gives x is 1883 divided by 595. What does it give, please? 3 point something? Is it 1? 3.16 from B. Again, ask yourself, does it make sense? Does it make sense? It does, because look here, the moment at B is 18, yes? 18.83. The moment at D is 1092. Yeah? So can you see this moment here is about a third of this moment? About half, sorry, isn't it? So any values, so you wouldn't accept any values, first of all, bigger than 5, okay? And just by looking at the moment values here, you can roughly say it's about a third of that. Okay, now let's plot. We finished AB. We're going to do the same for BC. So we finish with AB. Okay, so we do the same. We are going to repeat everything here. We've done everything we did for member AB. We are going to repeat it for member BC, for this one here. Okay. Any questions, please? Any questions? Okay, so member BC. So this is member BC. Okay, here, that's member BC, right? So I'm going to copy it there. So we have 1883, we have 2659, we have a UDL of, what was it, 2 kilonewtons per meter, okay? This is B and this is C. So we have reactions, we have reaction at A, at B, and we have reaction at C. So we call this here VBC, and this reaction is VCB, and we have a span of, was it, I forgot, 12 meters. Is that okay? Yeah. So we are going to, the only difference, we have a UDL here. So it's a little bit trickier, but otherwise the principles, the steps are the same. So we take moments about C, and then we take moments about B. That will give us the vertical reactions, which will need to add up. We have, we need to, the two reactions must add up to 2 times 12, 24. Clear? Okay, so let's do that. So take moments about, shall we start about B, for example? Okay, let's start about B. So about B, so we're taking moments about B, okay? Focus here, concentrate on B now. So moments about B, clockwise we have the 26.59. Anything else clockwise about B? The UDL, do you agree? What's the moment of the UDL? What is the moment of this UDL about B? What's the resultant? What is the resultant of the UDL? What's the total? How much is the UDL? 2 times? Yeah? So 2 times 12, 24, and it will be in the middle, isn't it, the resultant? Yes? So it's 2 times 12 times the distance, 6. So we have 2 times 12 times the distance, 6. I think that's it about B. That's everything clockwise, isn't it? So now we have anti-clockwise. That's clockwise. So now anti-clockwise, we have the 1883. And we also have this reaction here. So VCB times 12. And that's it. Okay? So you just need some concentration when you write down your moments by making sure that you put the moments in on the right side of the equation. Clockwise equals anti-clockwise. And if you have got a calculator, please, can you do it quickly? And I can give you the answer. I've got VCB 12.6 if you want to check it. Please do check it, that you know how to do it, okay? So we have VCB, please do check it, is 12.6 kilonewtons. I hope you all know how to manipulate the equations, yes? So got the, everyone got the 12.6? Please, yeah? Thank you. Now we do the same, we take moments about C. We have, about C, we have clockwise about C, I have the 26 here. We have the reaction as well. We have the VBC times 12. And I think that's everything clockwise. Then anti-clockwise about C, anti-clockwise, we have the 18.83. And we also have the UDL about C, is this time the UDL is anti-clockwise. So it's 2 times 12 times 6. And please, again, do check the answer. I've got 11.4. Yeah, and check now the vertical equilibrium, check. So we check VBC plus VCB is 11.4 plus 12.6, 24, which is equal to 12 times 2, and that is correct. Okay, that's the UDL, 2 times 12. So therefore, we are 100% confident that the reactions are correct. Very easy to make mistakes. I keep saying this. If you make an error here in the signs or whatever, you get wrong values. If you don't do that, if you don't take 2 moments equations and then check like that, there is no way you know when you have gone wrong. Okay. Any questions? Okay. So now we're going to determine the intermediate values here, the points of contraflexion, and the maximum moment. Any questions? Okay. So intermediate values. So intermediate values. In order to determine the intermediate values, what do we need to do here? Again, take a section, take a cut. Yeah. So we take a cut or a section. So I'm going to take a cut here. Have you finished with the reactions, please, everybody? Yeah, thank you. So I'm going to take a cut here, there at some distance x. Okay, so I take a cut at a distance x. Please follow with me carefully, okay? So we need the bending moment at the cut here. Okay? We need the bending moment at the cut. Okay, now, tell me please, what is the bending moment at the cut here, M? VBC times, yeah, and we know VBC, isn't it? That's 11.4, yeah? So we know, so it's 11.4 times x, yes? Then what? Then we have the 1883, which is minus, yes? Anything else? Don't forget the UDL. We have the UDL here. We have the UDL there. What's the total UDL on that portion? What is the total UDL on that portion here of the beam? It will be 2 times x. Will it be positive or negative? Yes. So minus 2 times x, that's the total UDL, times the distance. What's the distance? Now look, this is x. So x over, that's it. That's the equation of the moment, okay? Really, you need to concentrate, please. It's not difficult. All you do is you take your cut, cover the rest of the beam, and look at what the moments of each individual force is about that cut, okay? So you have 11.4 times x. Then you have got this moment here, which is hogging moment, so it's minus 1833. And then you have got the UDL itself on that portion only of the beam, on that portion of the beam. So it's 2 times x, that's the total UDL, times the distance, which is half of x. Clear? Okay, so we have 11.4x, 18.83, and 2 over 2, the 2 and the 2 will cancel, isn't it? So we have x squared. I'm going to rearrange it as this. Okay, that's the equation of the bending moment expression at a distance x from B here. Is that okay? Yeah. Now we can start answering the questions. What are the positions of the points of contraflexion? What is the maximum moment? Now we need to remember some definitions here. Which one do you want to, shall we do the maximum moment first, and then we do the points of contraflexion? Okay, maximum moment. What is M max? Okay. Have you all done a previous structural mechanics or structural analysis module sometime? Okay. The maximum moment corresponds to what? Yeah, I did kind of say it. I think I did say it last week, a little bit last week. The shear zero, isn't it? Because if you remember what we said last week, we said if you know the moment, the relationship between moment and shear is that if you differentiate the moment, you get shear. So from a purely mathematical standpoint, that means that the maximum moment corresponds to 0 shear. So when the shear is 0, you've got maximum moment. Okay? So therefore, that corresponds to shear, the shear S being 0. And the relationship between shear and bending, I've just said it now. What's the relationship between bending and shear? What's the relationship between shear and bending? I've just said it. Sorry? Sorry? Derivative, isn't it? Yeah, you differentiate. If you know the equation, of the bending moment, which we do here, then the shear is actually the derivative of m about x. You differentiate it. So therefore, we have S equals, can you differentiate this for me? Minus 2x, yes. Exactly, thank you. Yeah, easy, okay? So we have minus 2x plus 11.4, and all I need to do now is put that shear equal to 0. So Mmax means S0 minus 2x plus 11.4, and that means that 2x is equal to 11.4, which means that x is 11.4 over 2, giving me, is it 5 point? Yeah. Okay, so that gives you the max. I'm just checking that. Yes, I've got the same. So we've got x equals 5.7 meters. Remember, this is from we're taking the origin here at B, so it's from B. Okay. So we've got that. We've got x. We haven't got m yet. So now please, can I have your attention, please? So now we've got x. All we need to do to get m max is back substitute x into the equation of m. Okay, so you take your value of x, substitute it into m here, and that will give you this maximum value we are looking for. Okay, so we have m max is equal to minus 5.7 squared plus 11.4 times 5.7, okay, minus 18.83. And that's it. I've got, please, can you check it, please? I've got M max, I've got 1366 kilonewton meters. Thank you. So that's the maximum moment. Okay. Now look here. If you look at this beam here, these two moments are hogging moments. They are negative moments. This moment here is positive. It's a sagging moment. So if you are designing, if this beam here was a reinforced concrete beam, you will design it for the maximum negative moment, for the to get the negative reinforcement, and you will design it for this moment here for your positive reinforcement. It's everything we are doing here is really has got a an impact of what you're doing. If you're designing these beams as a reinforced concrete beam. If they are like steel I-beams, it's not that important. The size are not very important if you are designing a metal frame, if you've got steel, yeah? Because steel behaves the same in tensional compression. You know that, okay? So steel behaves the same in tensional compression. It's not the case of concrete. Concrete behaves differently in tensional compression. It's a lot weaker in tension, okay? And it's stronger in compression. So the size are very, very important when you're designing structures made of concrete. I think you will do that, hopefully, when you do your design module, okay? So you've got that. The only thing left now are the points of contraflexion. So the points of contraflexion, we have, so we're looking for these points here. And we know there are 2 points. We know that. So we're looking for 2 points. Now, the points of contraflexion corresponds to moment equal 0. All right. So here we have m is 0 this time, And therefore, we have got this equation here. We have minus x squared plus 11.4x minus 1883 equal to 0. What we have here, we have a quadratic equation. Yeah, we have a quadratic equation. How do you solve a quadratic? Do you remember how to solve a quadratic equation? Or no? That's like GCSE. Do you remember the ax squared bx plus squared b squared minus 4ac? Does it ring a bell? Yeah. I mean, this is the form of this is ax squared plus bx plus c equals 0. A is minus 1 in this case. B is 11.4 and C is minus 1883. Okay. So this is the form of the equation, ax squared plus bx plus c equals 0. And then the solution, and then you calculate delta, which is b squared minus 4ac. Okay. What is delta in this case? (11.4 squared minus 4 minus 1 times minus 883. Okay. Please do check my answers because I've got a delta of 5464. That's what I have. So yeah, so you do b squared, 11.4 squared, okay, minus 4 times minus 1 times c, ac. Okay, so b squared minus 4ac. And then you have two solutions. We have two solutions. We have the first solution is x minus b plus square root of delta over 2a. That's number one. And the other section, the other solution will be minus b minus square root of delta over 2a. Right? This is the solution. These are the solutions for a quadratic equation. When the delta is positive here, you've got two possible solutions. One is with the plus square root of delta, and the other one is minus with the minus square root of delta. Okay, so you substitute minus b here. You've got minus 11.4. You know the delta 2a. A is minus 1. And if you do that, please again check. I've got solution x equals 9.4 meters and x equals 2 meters as the two possible solutions, both from point from B, from the origin at B. Is that okay? Are these solutions acceptable? Are they acceptable? Yes, because that's less than 10, and that's also less than 10. Yeah. Just be careful because sometimes you have a quadratic equation. We'll see with some examples where you have a quadratic equation and there is only one point of contraflexion. So what you find that one of the solutions actually doesn't, is not acceptable, either because it's going to be negative or it's going to be larger than the span of the beam itself. So always check that your answers are acceptable and make sense. Okay. Okay, any questions, please? Any questions? Sorry? If you want to, oh, it's being recorded. You're not? I'm not sure. If you're not on the Teams group, or you have not been, or you're not enrolled correctly yet, I know some students are still using their private email because they're not on the system. Drop me an email, please. Send me an email, and I will add it to the Teams. No problem. Okay. Anyone still not being enrolled properly or not in the channel, on the Teams channel, please let me know. Okay, and I will add you on. Okay. Now, so we've got everything. We've got the points of contraflexion. We've got the maximum moment for both beams. So therefore, all we do now is actually finish the diagram. And what I have here here we've got the values calculated and the points of contraflexure, and everything has been determined. And that's the fully annotated bending moment diagram for this beam, fully annotated with all the moments at the joints and all the intermediate values. And if you want to design this beam, that's all the information that you need. Okay, so we've done here an example from A to Z, typically. Yes. Oh, sorry, yes. Have you got any questions on any of the calculations here? Okay. I will scan the sheets and put them in Aula as well. Okay, so you'll have the recording plus the lecture notes together. Okay. Are you all done with the top bit here, please? You done? It's okay. Okay, thank you. Right, okay, so I just want to show you this before we finish. That's the bending moment diagram with all the values shown. Okay, any last questions, please, before we finish? Yeah, thank you very much. I will upload, to help you practice, I will upload a similar question where you will be working on your own, and then I will reveal the solution maybe by Friday or Monday at the latest. Is that okay? Okay, thank you very much. And see you next time, okay? So I'm going to stop the recording. Thank you.